you, thank you. All right. Oh, yes. So this is the page fault liberation army. We're in the business of showing what's really inside the neglected bits of the Intel processor. We are going to start with a bit of philosophy of why we do this, because this has been a line of research in our lab, and as you can see, it's turtles all the way down. And then we'll hit the actual details just about halfway through the talk. No instructions were harmed in the making of this talk. Our great thanks to the wonderful Intel hardware that allowed us to have all this fun. We're going to talk about Turing completeness, and people really overvalue Turing completeness. You can do interesting computation with systems that are not Turing complete. It's just that Turing complete is the most general you can do. And it's really, computation-wise, something like the root shell. So if you can prove about a few instructions that together they make up a Turing machine, that means you can do anything there that you can do with the regular processor, say memory, reading, writing-wise. I wish we had a better scale to talk about exploits and, you know, the kind of interesting unexpected computation, but so it goes, but, you know. The slogan for the day is that any input is a program. Any input that is sufficiently complex is really just like the bytecode to the code that processes this input. And every exploit is an exercise in programming that weird virtual machine that you find in your target. And it really just doesn't matter what its input. Our introductory example is ELF metadata serving as a program that can actually arbitrarily rewrite memory. So if you think of how you load your code, you've got the symbol table, and you've got the relocation entries, and together the RTLD reads them, and based on what you find in the symbol table and the relocation entries, it rewrites your code and your data. So you see one piece of code reading the input and the other writing into memory. So you ask yourself, what happens if the writing would go right on top of the data that is being read? Well, if you've been through a traditional computer science course, this should remind you of the tape of the Turing machine. There is some finite state automaton that reads and writes to the tape, and the contents of the tape are the program. And the contents of the tape at the same time get transformed. And this is the most computationally capable thing which is like unto a modern processor. And so you ask yourself, what happens if you take the symbol table entries and the relocation entries, which are just C structures that are embedded in the binary, and you write a program in these structures alone? Since you see, you can read and you can write into the area that your next read will come from, that might actually give you all sorts of interesting loops and branches. As the relocator goes through the relocation entries and patches up the code that's not loaded at the address where it was meant to be loaded. If you're using ASLR, then you know this. This is how your program gets relocated. And there has been a great bit of wonderful hacker research in using this for obfuscation, in using this as a sort of an unpacker of a code. The most basic observation is that those relocation entries contain full arithmetic. So they have all the different types. You see the types in the table on the right. And that type drives either a memcopy or a memory write with addition and lookups in the appropriate data structures. So you see the structure of the byte code in the input. You see that this type byte in blue actually drives something like a virtual machine. And these relocation types are like the implementations of the opcode of that virtual machine. And this was done by Rebecca Shapiro, Bex, in our lab. If she is here, I can see, I'll let her wave.
Nope.
Nope. Okay, then. And you can see that you can see the tools and the details of how all of this is implemented in her repository on GitHub. But the takeaway is that, look, once the data is complex enough, it's really just like the byte code. And so it doesn't matter whether that metadata is read by software or by hardware. So we're going to show this, the very same effect for the processor, for the internals of the processor that you would imagine to be part-way microcode, part-way silicon. And so, who's this guy? He is regarding this kettle swinging on its chain over the hearth because of that little blow of steam coming out of the kettle. What is named after him?
A unit of energy.
The unit of energy. This is James Watt. He was berated by his elders for just wasting his time looking at kettles. And of course, he built this. And we're going to push this as far as it will go. And hopefully, when we run into an obstacle too high for us, other people will take over. This is somewhere in Siberia, as you can imagine. Well, and we'll let you build a snowplow that can get through all of those snowbanks. So, consider the x86 MMU. People are taught to think of this as some sort of a lookup table, virtual to physical. It's just like a lookup table only in hardware. It's not. It takes complex data and performs complex logic on it. It's got states and transitions. Everything that's got states and transitions is something like a processor, maybe a weird one. It's an automaton, it's a machine. And so you ask yourself, well, if this thing takes complex input data, can it be programmed with that input data? MMU operations are write memory. They also read memory. You've got the tape. So every time, we need a drinking game, right? Every time I say input, well, can drink on stage at such a fancy hotel. So why do this? We are looking for the actual computational models of computers that surround us. The classical computer science proved theorems about what is computable. Church and Turing, the founders of the field, did that for us. But then computer science went away from the question of what is computable on any particular platform and started doing other important things, whereas hackers remained in that niche and built programs, weird programs called exploits, for platforms doing things that the platform was not meant to do. And that's really why we do this. We're eliciting what actual computational model is in the machine. And so let's take a look at the CPU with its memory management unit. As you might be aware, if you know x86, there are various tables that drive the memory trapping in the and memory translation in the protected mode. So interrupt descriptor table, the global descriptor table. Interrupt descriptor table is where you find the addresses, the vectors for things like the page fault or the double fault that happens when you fail to dispatch a page fault. Then you have the page tables with all sorts of interesting bits scattered through them that cause the trap, that cause the page fault to fire. And most importantly, when you have a fault, you write bytes onto what the MMU, the CPU, thinks is the stack. So a page fault handler needs to leave some information about the fault in the memory. Now, what would happen if that memory was where the tables that you're reading from are? You could put the processor into a sort of a weird loop in which no instruction is successfully dispatched, where every step that you take causes either a page fault or a double fault. So long as you formulate your tables, the GDT, the page tables, the IDT properly, you can never leave this loop, it turns out. You can use your tables that describe the memory translation and drive the MMU as the input, as the program, borrowing bits and pieces of the MMU logic, and it turns out to be Turing-complete, as we hope to show, to convince you of. So this situation is exactly the same as the ELF example from our previous talks that we started with. Again, you have input, and that is read, and you have the ability to write memory, possibly all over that input that is read. And so you have the beginnings of a Turing machine. And then it turns out that the logic in the MMU is complete enough to make this an actual Turing machine. So, and you know, this is the principle. Now let's take the deep dive. You can actually order that T-shirt with
apologies to Intel.
With apologies to Intel. I mean, we never meant to impugn them in any way. They let us have all this. I mean, they make all these processors that let us have all this fun.
Indeed, and so first I'm now going to give a quick overview of the various twigs that we're going to glue together horribly into making our terrible, terrible Turing machine that runs without any CPU instructions. And the first step is that we're going to go back in the old dark days of DOS, before in the 286 and 386 days, when people were beginning to write multitasking operating systems for the Intel processor. The first virtual memory system that Intel implemented is the segmentation-based system, which is nowadays completely unused. The only real multitasking OS that ever used it were some old versions of OS/2. However, for backwards compatibility, this has always been present in the processors, and hackers have always found this unused mechanism and made it do clever things. And so it's actually still a valid memory translation mechanism, and it's the first step that happens from every virtual address on its long way to becoming an actual physical address on the RAM bus. The segmentation mechanism is driven by the global descriptor table, which is a table that can be located anywhere in memory and just contains 8-byte wide entries describing segments. Segments are tagged or typed regions of memory. They contain a base address and a size, just a range of memory addresses. However, they also contain an often disregarded type field, where you can specify if something is meant to be a stack address or a data region or some piece of code. And then there are various registers in the processor core that allow you to specify which segment is supposed to be used for code fetches, what is supposed to be used for stack addresses, accesses, and so on and so forth.
And long story short, this is what makes the rings 3 to 0, the bits in those descriptor entries.
Indeed. And afterwards, Intel added a second memory protection mechanism that is the one that is actually used in all the operating systems we use day to day, including this MacBook running the presentation software. That is the traditional virtual memory system backed by page tables, where there is a multi-layer hierarchy of tables that both provide a lookup table or translation function from virtual addresses into physical addresses. However, they also contain 8 very interesting bits that specify what this memory is supposed to do. For example, if this memory is supposed to be accessed by user mode code or by kernel code, and whether it's supposed to be read or written to, and in newer extensions of the architecture, whether it's supposed to be executable or not. And that gives us all these rules that need to hold on the page tables for memory access to successfully go through. If any of these rules happen to be violated, the processor interrupts execution and traps into the kernel.
And so we hit the page fault. The page fault is just about the most overloaded, the most hard-working interrupt descriptor table entry ever, because so many hacker hardening patches have used it, have placed their bits of logic over that. Because really, you can't enforce a policy that you can't trap the events that are relevant to. And so we're going to go through a few of those examples, because those were really the inspirations for the bigger thing.
For work. And the first project that we drew our inspiration from is the OpenWall project by Solar Designer back in 1999. What Solar Designer wanted to do is he wanted to prevent the very simple stack overflow attack presented, for example, in the frag paper, Stack Smashing for Fun and Profit. And it made use of the fact that there was this unused segmentation mechanism sitting in the processor that was there and was in the silicon and the microcode, however, no one was really using it. Traditionally, the segmentation mechanism was completely disabled by just loading all of these segment registers with exactly the same value that just made them an identity transform. While it has the feature to both remap memory addresses by adding an offset to them and limiting what memory regions are valid by comparing them against the limit. What OpenWall did is it set the limit of the code segment to just below the end of the user space addresses, leaving just enough space for the stack at the top of the user addresses to not be in the code segment. So whenever you would have an instruction fetch from the code segment, that would cause a page fault or a segmentation fault, whereupon the kernel would check what the last executed instruction was. And if it was a return, it would see that, oh well, you just returned into stack memory. That's probably going to be bad. It turns out that GCC, under some weird conditions, emits code to support fancy languages like Objective-C that actually will return to the stack. So they have some hacky workarounds there to still support that legacy code. But that way they can defend against that one very specific attack of return to the stack.
This was the first non-executable stack, the first stack which actually overloaded the trapping mechanism to do policy, to do hardening. The next one was PAX. And PAX is really just this amazing encyclopedia of all the things that you can do with a processor, such as it had the emulation of the NX bit before the NX bit actually appeared in P4, and it still maintains it on a whole bunch of processors that don't have that. And just what happened there was a very creative view of the memory translation look-aside buffers. This is the entry for the, this is the page table entry. In the page table entry, the blue bit, is the user supervisor bit. That was used to model the non-executable bit and trap on trying to fetch code from pages where this bit was set. So the Intel CPU, MMU, has two separate silicon paths. One for fetching instructions, the other for fetching data. And there was an old process called Plex86 that tried to use that to detect self-modifying code, and this is where the creators of PEX got their inspiration for the page NX. They're using the data TLB, the DTLB, and they're using the fact that it can be desynchronized from the page table entry. So the TLB contains the latest successfully translated page table entries for faster lookup. Of course, if every lookup had to go through the page tables, you know, you would pay with 3 or 4 memory accesses per one memory access. That wouldn't do. So that's why once a reference succeeds, it gets lifted into the TLB. And if it was a data fetch through the data segment, for example, it would be lifted into the DTLB. Now, the user supervisor bit was supposed initially to protect supervisor data from being seen by users. But they built this ingenious scheme that actually uses the hardware logic of the TLB translation. It's an additional automaton to enforce policy. Just think about how wonderful this is. You've got this extra state in the processor because there are actually physical bits. There is a copy being made, and you use it. And the way it worked was like this. A data fetch has to go through the DTLB. An instruction fetch has to go through the ITLB. Okay, so when you look up an address in the TLB, you have a copy of the page table entry, if you've seen that memory before. And if the user bit is set, then you get the access. You just sail on through. This is a normal data access through the DTLB. If the page table entry is not in the TLB, then you have to walk the page tables. And you always set that bit to 0 in the page tables. So it always causes a fault. So when you, remember, when you're trying to, say, jump to that address or fetch from that address, the PTE, and you don't have that in the TLB, the PTE will cause a fault because it always does with this setting of the bit. Now, you hit the page fault handler. Now, something bad occurred. The page fault handler steps in, and it examines the EIP. If it is an attempt to fetch an instruction, a jump to an instruction, then you terminate. You've just tried to access the non-executable bit. You try to fetch from a page with the emulated non-executable bit set. If it's not an instruction, then it's normal data, and you perform 1 byte read. Just before that, you set the user supervisor bit to 1, which allows this byte read to succeed. That populates the TLB, lifts the entry into the TLB with the right user bit set. Then you immediately unset it. So you've desynchronized your page table entry, which always causes a fault, and the DTLB entry, which never causes a fault, which allows the accesses to sail through. The additional beauty of this is that you lose performance on the page table entries. But you don't lose performance on the TLB lookups because the TLB always has the valid setting of this bit. And it's just the page tables that has the setting that allows you to examine what that memory access was, a fetch of an instruction or a data reference. And you keep them desynchronized. And once that technique was understood, a whole bunch of interesting uses of it arose. For example, there was an Olibone, a plugin for Oli Debug, that allowed to trap on this complicated condition that the code, a page just written to, was fetched an instruction from. So the decompressor or the obfuscator just finished working. The unpacker just finished working. And now the code that it unpacked is being jumped to. This is emulating a trapping condition that x86 does not support. But it was done with this desynchronization of page table and the TLB. But, of course, you ask yourself, if you really want to be evil, then why stop at setting manipulating one bit, this US bit? You could actually unset desynchronize the physical page frame that you are referring to. You can get a different physical page frame into the TLB versus the page table. So what happens then is that if you access that page as code, you go to one page, one physical frame. If you access this as data, say if you're an antivirus and you are scanning it for badness, as hopeless as this task really is, you just get a different page because the TLB entry is desynchronized from the page table entry, from the actual page table entry, and you are just basically getting a different thing. And so what we see here is design patterns, something worthy of the name, in which those trapping bits are used as labels, as tags, spread through several places in memory, and causing the trap at just the right condition, and the page fault handler being there to pick it up. And so that way you can combine traps to have an and or conditions, trap on this and that, which again the MMU doesn't give you. You can label data. UDREF plugin of PAX uses that to prevent the kernel from reading user data. If you saw Nikita's talk, then this is one of the ways to attack the kernel that he mentioned. Intel is introducing the SMAP features into the processor that make it easier and more efficient, but PAX had it before. It was a way of tagging pages by intent. The insides of your kernel are not supposed to look at your user memory. Only a small piece of your kernel that dispatches the syscalls has any business looking into that when it imports the arguments. So it's really coming back to the old tagged architectures where memory was not just bytes, where you could say which bytes in memory served which purpose. And the NX bit is just a tiny little step towards that. As you can imagine, there are all sorts of data flows that you want to block only if you knew what all those bytes that are totally created equal in memory are meant for. And the only way to do so is to create a tag, a label for pages. You can't do that, but you can spread that through the trapping bits. And as you overload the page fault handler, you can then make sense of those and trap the undesirable flows. So this is the inspiration. We thought that there is a reason why all of this worked. And the reason is that there is enough computational power in the MMU. And we asked ourselves, well, how much? What can we program with that input? And with that...
and that gave us a whole lot of twigs that we could potentially build a machine from, all that state. However, we also needed some mud to glue it together. And that's where the mechanism that actually implements the trap handling comes in. The way that the kernel gets from normal program execution into executing that all-powerful page fault handler. On Intel, there are in fact 3 different ways of handling interrupts and conditions. 2 of them are very similar, and 1 of them is by now completely unused. The typical way that all modern operating systems use for day-to-day interrupt handling is called a trap gate or an interrupt gate. If you've ever programmed in the old days on DOS in protected mode, it's similar to a fault jump. You just specify a new code segment which usually would be the kernel's code segment, thereby causing a transition from ring 3 to ring 0, and an address within the kernel. That's just like a regular function call. And in fact, Intel tries to be nice to operating system developers and makes this behave just like a regular function call, which on x86 involves parameters being pushed to the stack. There is a special configuration region in memory that I'll get to later on that actually contains stack segments for each ring, and if you switch to a different ring, like from ring 3 to ring 0, the process's microcode will be nice enough for you to look up where your operating system kernel stack is supposed to be, and will push various values about the old state of the execution to the new stack frame, which you can then just use like regular function arguments in your page fault handler. However, this makes quite a few assumptions about the state of the processors. For example, that task state segment has to be set, that contains the information about where the kernel stack is, has to be set up with a valid stack. The code segment that is specified in the IDT entry has to be a valid code segment, and various rules about the rings being transitioned have to hold. And also, the IDT entry has to be there in the first place. All of this could potentially fail, usually only when there's a kernel bug. And Intel has a special mechanism for handling such bugs named the double fault. The double fault is when you have any sort of error condition occurring while trying to get from execution to the interrupt context. However, if the first instruction of the interrupt handler itself fails, that's not a double fault, but just another page fault, which is a fact that we'll that allows us to actually keep looping on faults for our machine.
So you see, there is this situation with the chicken and egg. In order to handle a memory fault, you have to be able to write to memory those bytes that go on the stack and describe the condition. Well, what if you can't write to memory? Well, you have a deeper fault. And then, of course, even that may fail, because that also needs to write memory and read from memory. So then you go into the triple fault, otherwise known as reboot. But, you know, in order to catch a fault, you have to cause a fault. There is a beginning of a clock in there. You will see that we will learn to oscillate between the page fault and the double fault as if this were a processor clock.
And that's where Intel's hardware task switching mechanism comes in. Nowadays, on modern operating systems, this is only used for displaying for displaying a blue screen of death or kernel panic as the last resort. But in fact, it is a very well-designed mechanism that allows you to save and later on restore almost all of the processor's context, at least the way it was in the 386. You do this by specifying a special kind of entry in the interrupt descriptor table, which does not contain an address like the regular trap gate does, but only a selector for a task state segment, or TSS, which is an index into the global descriptor table that we saw earlier with the old segmentation mechanism. And in there it will point to this large region of memory, 104 bytes long in 32-bit mode, that contains all the registers of the processor. And the CPU's microcode has features for saving all the processor's state into such a region, and for restoring all CPU state from memory.
So now you're seeing the pattern. You've got the fault, which can actually switch tasks, which can actually write all of this a large block of information, and it can actually write it wherever the table, the GDT, is pointing to. So you see, you can really just write over the memory that you are reading, and that is driving the next step of your fault dispatching. And this is exactly what we're going to use.
And the actual micro program that is running while switching to the task is that at first, when an interrupt occurs and a task gate is specified in the IDT interrupt descriptor table, the CPU will save all of its state to the location pointed to by special register, the task register. On Linux, this is actually the only piece of this entire mechanism that is actually used. During boot up, the kernel at one point sets the task register up to contain a somewhat valid task, so it is able to handle double faults and print a panic message, and afterwards the entire mechanism is forgotten about.
So think of this as a dark silicone that is dark to Linux, but is the very bones of our page fault liberator.
And it will then walk all of these in-memory tables, find a new task, perform some basic validations on that task, and actually check if there is if this task has already been used before with a so-called busy bit, because they want to prevent looping. And we'll get back to how we work around this. It will then load all of its state from memory and push the error code to the stack, because there might still be some other parameters that you want to save about the previous execution state, so it actually pushes 4 bytes to the stack. And it will then begin executing the new AIP. However, that is after the entire interrupt handling logic has occurred. And if that new EIP happens to be at an invalid memory location or any of the page table constraints are violated, that will just cause another page fault and not, in fact, a double fault. And here I'll have to insert a brief digression, a true gem that we found in the Intel manuals. In one of the dark and musty pages that no one has probably looked at in the last 10 years, because again, this mechanism is not used in our printed out tome that contains a description of the Intel processor. It specifically warns against placing this task state segment on a page boundary, because the way it was apparently done on old processors is that the processor looks up the physical address corresponding to the first byte of this 104-byte long TSS, and then reads 104 continuous physical bytes from there. At the time, this was not a security problem, because to access any of these data structures, you had to be in the kernel. And if the kernel could perform reads to physical memory, well, it was no problem, because the kernel is designed to do that. However, what we were thinking at the time is, wouldn't it be nice if you had a virtualized environment, and you could place a TSS on the last byte of a page somewhere, and then read 103 bytes that on the next physical page? If you manage to get enough fragmentation, that might be a completely different VM. And we were quite excited that we had found a sleeping dragon there, and we're making plans to, own all of EC2. However, then we did the whole science thing, and the reality check came in, because by now, Intel CPUs actually translate this double word by double word and perform the safe thing, which again is an because this mechanism is no longer used, the optimization of reading 104 continuous physical bytes is no longer necessary. So this has been pushed off somewhere into the microcode where it's safely done. So instead of a sleeping dragon, all we had is a sleeping manual. However, as is the tradition, cats can also be quite interesting, and this fact, in fact, allows us to build our computer out of twigs and logs.
Some of us maintain that cats are more interesting than dragons.
Oh, so they say. Taking a little bit of a step back, usually when people talk about Turing machines, they talk about things like tapes and finite state machine and a lot of complicated logic. But in fact, you don't need all of that. All you need is a single CPU instruction. That CPU instruction is a little bit convoluted. It's, in theory context, they talk about decrement and branch if negative. There is a wonderful book on this that if you have access to an academic library, you can easily get. However, if you intend to purchase it for yourself, it is a tiny bit expensive for the amount of information contained therein, and Wikipedia provides just about the same things. The instruction is just that you have a finite set of, or if you want it to be Turing-complete, a theoretically infinite set of memory locations, and you decrement any one of these memory locations and branch to one instruction if you have an underflow, to another one if you don't have an underflow. To make this practical, we also add a move to our one instruction, because in a simple decrement and branch of negative architecture, the way you do a move is you overflow integers, which tends to be quite bad for performance if you actually want to do a demo. However, the move, that's not a problem. And now we'll go in and introduce the various actors in our implementation of the Turing machine. The EIP register of the processor will always point at invalid memory. So
F.
0. So at no point will there ever be a valid CPU instruction be executed, because there never is a place where the CPU could actually fetch a memory instruction. It always tries to, then sees, oh, okay, let's handle an interrupt, do some of its microcode magic, and then just to drive into another wall. Or actually the same wall, but with a slightly different internal state. To get our decrement, we use the fact that this 4-byte error code is pushed onto the stack. So we have, for each memory location, we have one such task state segment, and pushing that error code decrements the stack pointer value at that location by 4. And the branch is if it's less than 4 bytes or not. If it's less than 4 bytes, the stack push would fail, because the stack there's actually a separate interrupt caused by having the stack pointer wrap around. Thereby, we would cause a double fault. If the decrement succeeds, or the push succeeds, that would be another page fault. That's how we get our branch. We keep a single global descriptor table around that will describe all of these structures. However, we'll use different page tables to map different things around at runtime, so we can have a larger number of instructions than would be allowed in that relatively small table.
In particular, one TSS descriptor per instruction and one IDT per instruction. That turns out to be a necessity of bouncing between the page fault and the double fault, whose addresses are contained therein.
Indeed. And because the TSS allows us to switch out page faults, we always put our target for branch not taken into the interrupt 14 page fault location, and we put our target TSS for the taken branch, that is an underflow, in the interrupt 8 location. And by remapping memory through the instruction switch, that is loading memory, what the interrupt handler does is it loads memory from one virtual address and then saves it back to that same virtual address. However, in the meantime, it switches out page tables. So while it may be writing back to the same virtual address, we can map that same virtual address to a different physical address, thereby also giving us a free move through changing that remapping function.
When the instruction changes, the world changes. The view of the entire memory changes with the specially formulated page table. Well, we might go to the demo.
Yes, indeed. And luckily also, the TSS contains a whole other bunch of bytes that will be written and read and written from memory, which allows us to avoid some of the unfortunate implementation constraints that the real silicon has, so we can work around some problems. And to keep you interested, we have prepared a little demo, which is what we believe to be the world's most efficient implementation of the game of life, because it uses 0 CPU instructions to date. Would you mind unscrewing that cable?
Cable unscrewed.
Perfect.
We have connection.
I made my sacrifices to the demo gods last night at a bar. I hope they still hold.
All right. Now it's booting.
Okay, so what this does is it first executes some normal kernel code that will set up all the tables in the correct way. I have released a tool that automatically generates the C code that will set up the tables in the proper way from a more sane intermediate language. And that will then cause a single page fault, which will compute an entire iteration of the game of life. It will then use that same double fault mechanism to restore sanity briefly and execute a series of move instructions that will just copy things from all over the memory into the VGA frame buffer, and then just cause another page fault at the end of that instruction stream, which will go back and compute the next iteration of the game of life. In fact, those of you wondering about how performant this might be, this also includes a massive delay loop that burns something like 500 million cycles between each iteration. If you run the undelayed version, you don't see anything, you just see a white box or a white band. And now let's go back to the talk.
So let's see how this works, right?
Indeed. And if there's one trick that I learned from Sergey, it's that occasionally while teaching you have to lie. So we'll begin with a small fairy tale version of this and then slowly introduce all the implementation constraints that we have to work around, and oftentimes we use fairly excessive methods of violence to deal with various implementation constraints. So as Sergey has already mentioned, the instruction process of bouncing between page faults and double faults that we have is somewhat like the clock of a machine. In fact, the page fault happening is the rising edge of a clock. The first thing it does is write back the current value or the current intermediate value of our calculation into the output of the last instruction by saving the TSS state at the beginning of an interrupt. Then it will...
Remember, all of this is basically silicon or microcode, of course. But all of this is hard-coded in the CPU, in the MMU. So all you're doing is you're triggering those operations with your fault conditions.
Indeed. And then the CPU will proceed to load a new execution state from the TSS and attempt to save that fault error code onto the stack, which we just use for its decrement of the ESP. If that decrement fails, we raise a double fault, which will cause us to go back to the very beginning of the execution and save the TSS state again and cause another clock. If, however, it succeeds, we have just decremented the stack pointer by 4, and will then cause another page fault by jumping to an invalid instruction, again giving rise to another page fault clock. Going through this slowly, this would be the initial state. The CPU is set up relatively sanely with a stack pointer somewhere in kernel space, except for the fact that, and the task register that, for example, the Linux kernel has set up that just points to an otherwise unused region of memory. Except that the CPU, except that we have prepared an IDT and a GDT with the tools we have released, and something in the kernel causes a page fault. This might either be cleverly hidden somewhere that you clear one of the various bits in the mapping that maps the kernel into virtual memory, or you just jump to an address that's going to be invalid, like 0 or all Fs. That then causes a page fault, which will cause the CPU to walk the interrupt descriptor table. See, oh, this is an interrupt 14, so here we have a task gate going to task 1F8. First, for the task switch, we look at the task register, see, okay, currently we're running task F8, so we have to actually do the full switch. Where's task F8? Oh, that's in the GDT. Points to the first TSS entry. And so all of the state of the CPU is copied into memory from the registers.
Whoosh.
Also the manual says. And then it sees, okay, now we want to go to task 1F8 for the interrupt handling. Again, walks the IDT and the GDT and sees, okay, this is from the second TSS entry we have. Let's go in and load all of the registers whoosh from memory. Suddenly all of the world has changed. We have a new stack pointer, we have a new task register, we could even have a new EIP. In our case, the EIP is still going to be invalid because we don't quite want the kernel to execute yet. As a side effect of this, it also sets a busy bit in the global descriptor table, which will be quite annoying, as we'll get to in a few slides. Another side effect of loading a new TSS is that the page table base register, CR3, has been reloaded. So the entire view of the memory, and thereby the CPU's entire worldview, has suddenly changed. It's a new instruction, it's a brave new world. And so whatever the TSS entries in the GDT may have been, the first TSS entry might now, coincidentally in this example, points to the same TSS as before, but the second one now points to a completely different entry.
And so we can do branching between the two different instructions.
And because the second TSS entry, that is currently the current TSS entry, points to a different location in memory, the value that we just read before, the 0x4, will be decremented and then stored into that TSS entry, which is a completely different location in memory. As I mentioned, there unfortunately happens to be this busy bit. In the normal mode of operation, you occasionally want to return from interrupts because you would like your program execution to resume. So Intel, being nice and kind and not wanting everyone to screw it up as they did before in the days of DOS, they provided a special return instruction from an interrupt that will look at all these structures and restore the state of just before the interrupt and retry the last instruction. That means there is a chained link stored within the task state segments. If that link ever were to become a loop, it would become an endless loop, and Intel wanted to avoid that, so they added a busy bit specifically to prohibit anyone from looping interrupts. So and if this bit is set in the GDT descriptor of a TSS, it will actually cause another double fault. This actually, of the 10 weeks or so this took me to implement this entire mechanism, about 8 weeks for I spent about 8 weeks figuring out or trying out ways to clear that one bit. And I had crazy schemes set up, and they all failed. Until I realized that while playing around with a debugger and single-stepping things and reading the spec closely, that the CPU always saves the state before it attempts to load the new TSS. So what we do is we map the lower half of the TSS over to the GDT. If we pick GDT descriptors that just happen to be at the end of a page, the EAX and ECX registers that we can specify as part of the task will be written over that GDT entry. And if we carefully craft the EAX and ECX registers, they'll leave the same content in there, except that 1 bit will be cleared.
So that's a nuclear option. In order to nuke this 1 bit, we nuke the entire...
We nuke the entire top half of a page.
But hey, you know, again, all of this power comes for free from the MMU. You only need to set up the MMU to do this, and that's where the faulting comes in.
And this is the first fault in continuity of our little fairy tale explanation, because of this mechanism, suddenly all of these bits that were marked as busy before in the GDT are now marked as available, because they have always been overwritten when loading a new task. What the CPU will then proceed to do is, okay, it now tries to invoke the interrupt handler. So we're going to give it its 1 parameter, which will cause it to decrement the stack pointer. And then it tries to jump to that 1 instruction, which, however, still happens to be 0xFFFFFF, and therefore there will be yet another page fault, giving us another clock. In this issue, however, then we notice, oh well, the stack pointer is going to be all zeros. So we actually can't push again. So let's try having a double fault. It will then proceed to do the entire game again, except this time with the interrupt descriptor table 8, as opposed to 14 that we had before, where it will load a new state from the double fault and try to perform the same game again. As you may have noticed when I was speeding up and skipping through the slides, that's usually a good indicator that I'm lying again. Because there is one other nastiness that is in there. I mentioned it very much at the beginning, that the CPU only performs this task switching mechanism when you're actually switching to a different task. So you can never jump from one instruction to the same instruction again, which mathematically turns out to be a graph coloring problem. So either you can write a very generic algorithm that tries to graph color your instruction stream. I spent about a week attempting to do this. Or you can make your compiler just emit bogus instructions at some point and duplicate the same instruction in a few places so that graph coloring becomes trivial.
Now, imagine my horror. I'm a refugee from math. My degree is in math. I have a PhD, for God's sake. And of course, I run from that into the bit land so that I never see graph coloring, graph isomorphism, that sort of problems. And we find this weird machine that can be gained from the MMU, only to have my star student come back to me and say, look, there is this graph coloring problem.
This is what happens if you send people to...
You can never run from it.
And it comes back. And a slightly less convoluted view of this is if you looked at the hypothetical front-side bus, which of course now no longer exists because there's hypertransport and caching. But what it will actually do while stepping through this example is it'll write to the physical address 0x8, the FFFFF0, the initial state we had, then read 0x4 from another location, decrement that by 4, and write it to yet another location. And it will then read back the 0x8, the state it originally wrote back. That's just what a normal branch and decrement computer, which people apparently were building in the 50s back when gates were really expensive, were building, would look like if it had real memory attached to it. So in fact, we can compute just about any function we want as long as we mind a minor performance hit when counting on a clock and a massive performance improvement when counting instructions, while making it extremely hard for someone who does not have access to the FSB to figure out what precisely was going on. We have a few other restrictions in there. One of them is that you need to be the kernel to set this up in the first place. Then there is a runtime restriction that you can't have 2 double faults in a row or the processor will reboot on you. Again, I was doing graph things there until I realized that it was a waste of time and just inserted another bogus instruction that will just always succeed.
Sometimes you can cheat math.
It will come back at me, but so it goes. And our one instruction is somewhat awkward to use. However, I've written a few tools that might help you around this and actually allow you to implement somewhat useful programs like the Game of Life. The biggest restriction that we have so far is that you can only work with the stack pointer of task state segments that are aligned in just the correct way that we have. But I'm currently working on extending the tools so that it allows you a special read from, or peek and poke instruction, essentially, so you can read from arbitrary locations.
To put it in simple words, we actually have a compiler.
Don't call it that. I hate compiler writing. The other interesting side effect of this is that no simulator that I've tested implements all of this correctly. I've developed this on Box, so my particular compiler emits code that happens to run on Box, because occasionally I like debugging things, because we're fallible. However, things like VMware and Zen tend to crash and burn as soon as they see double faults being linked in interesting ways. Sometimes they just have an assertion that fails, sometimes they go off and do really wonky things.
And so, you know, red pills are interesting, but there are so many of them. With this red pill, you can actually compute the equivalent of what a processor can compute. That's one big, giant, huge, humongous, enormous red pill.
And so the takeaway for those of you who happen to be wearing white hats, where I don't see anyone, is that you should check your tools how they handle obscure and weird edge cases. The much more interesting takeaway is for those of you who happen to be wearing black hats, where you get a nice and big red pill, but then again, you can probably fix that red pill so it works just slightly differently in analysis tools. Or you can just use this as a really evil mechanism of transferring control if you have, say, a kernel rootkit. Because this entire mechanism actually allows you to restore execution to an arbitrary location in memory, using a mechanism that is completely not supported by any of the debugging tools out there. Even while it may not be particularly performant, you can use it to bounce execution between different parts of your code, while making it very hard for someone to trace what is going on.
Reverse engineers, be warned.
And for weird straw hats that don't fit either into black hat or white hat categories, we're just excited that we found another weird machine. And therefore, we're working on making it work on 64-bit as well, where a lot of this legacy cruft has been removed. That's where the idea of overwriting things with the stack pointer comes in. And of course, we're always working on extending this compiler thing we have, maybe even writing an LLVM backend.
Remember, it's not about the color of the straw, it's about the weave.
And then we thank you for so patiently listening to us.
Thank you. We seem to have 3 minutes for questions.
We have 3 minutes for questions. That gives us time for 1 or 2 questions. Anyone? Show of hands? Yeah.
Yeah, sorry. So have you looked at any examples of weird machines where things that you thought might be weird machines turned out not to be Turing-complete?
Plenty. In fact, most of the exploits never... I mean, take any exploitation technique. It borrows code, it borrows logic from somewhere, especially if it's entirely data-driven. So it borrows only as much as it needs, and no one really thought about those things till approximately 2000, when Hera on BugTrack generalized the return to libc trick and using Tim Newsham's chaining of stack frames for what later became known as the return-oriented programming, actually wrote that, hey, you can fetch any program like that from those segments into your borrowed logic. So that was the first time when the genericity, the general nature of this as a programming exercise was brought up in the hacker community. And the academic community, when this was framed for them by Shachamhova with his return-oriented programming paper, caught on when he proved Turing completeness. He proved Turing completeness of a particular version of libc, or rather of gadgets that you can borrow from that particular version of libc, and that made the academic community sit up and take notice. It's not about malicious code. I used to read all of those machine learning papers about how we detect malicious code. I'm like, good luck. It's not about code anymore. Finally, the threat model has changed. It's now malicious computation. And with computation comes the question of characterizing it. But really, you know, mostly you can do nicely with a large enough finite automaton or a push-down automaton. Like I said in the beginning, Turing-complete is just something like the root shell. You don't always want your exploitation to end up in the actual shell. Sometimes overwriting a few bits here and there are enough. But what actually gives you the power to overwrite those is the chaining, is the computational model that's contained in the input, which acts as a program. Another question, perhaps?
I believe we're out of time. How many
yeah,
seconds?
10 seconds.
10 seconds. Nice. Quickly.
Anyone
Do,
on the floor?
do I see hands going up? No.
Oh, well.
Feel free
Thank
to
you for
approach
listening.
them both as well for these 2 days. They'll be at the conference. If you have any questions, they will be around. Thank you very much.
So-
Thank you.
Thank you.
Take a couple of minutes to hook up the next speaker and set him up on stage, and we'll continue right immediately after that. So we'll be back in no more than 5 minutes, ideally. Okay? Thanks.
I got a song that I sing, and I can make the rain go anytime I move my thing.